Hello, welcome back now to lecture 10 of Advanced Quantum Mechanics. Let me remind you of where we are in the course. So we started with the Hamiltonian, and then we derived the equations of motion, the commutation relations, and the hermiticity condition. Now, what we saw at this level was that the commutator of the x hat and the p hat, j and I, is IH bar, Kronecker delta IJ, and this I is necessary. This tells us that we are working with complex vector spaces. See, when we then solved this to obtain the x hat as functions of time and the p hat as functions of time, etc., and the f hat, then there were linear maps. Remember, we said that everything in math can be viewed as a map, if need be, trivially. And so we said, okay, we need to solve for x hat of t and p hat of t, and we know they can't be number valued, so what can they be valued? Well, they're going to be map valued. And we found that, luckily, it suffices to consider the case of linear map valued x hat of p and x hat of t and p hat of t. So that's what we found. We solved this problem to obtain x hat of t, p hat of t, etc. as linear map valued functions of time. Concretely, these linear maps were matrices, right? Matrices are linear maps, but generally there could be any linear map. Okay, and these linear maps act on vector spaces, right? That's what linear maps do. And we know from up here, because there's this I in there, that those vector spaces have to be complex vector spaces. So what we did in the previous lecture was that we defined what is a complex vector space. So we defined complex vector spaces. Now, then we did the next step here, if you remember, and we calculated the number valued predictions, x bar of t, p bar of t, f bar of t. And how did we do that? Well, we introduced a psi, which is an initial state vector. That encodes, with the choice of psi, we are encoding the initial conditions for the problem that we want to solve. Now, what we observe here is we observed that when we spelled it out, we found that, for example, for f bar of t, where f is some polynomial in the x hat and the p hat, we found that its expectation value, the prediction for this value in our calculations, is given by psi star n, and then f hat of t, which in our case was a matrix. And later we will see that the psi doesn't have to be represented as a column vector and the f not as a matrix, but that's what we found in our first examples. And m, and and then here psi m, and we are summing here over n and m, which take infinitely many values because we are in infinite dimensional vector spaces, and this can be written compactly as psi dagger and then f hat psi in linear algebra notation, right? Where, what is this? This is, just to remind you of linear algebra notation, this is a column vector. And then that's, of course, a matrix. actually a matrix that's a function of time. And then what is this? This is a row vector whose coefficients are the complex conjugates of the coefficients of the psi. So this is a complex conjugated row vector here. And the whole thing is a scalar product. Right? We remember all of this from linear algebra. Scalar products being important because scalars are bases independent. We could calculate this expression in any basis, and the scalar product is the same numerical value. But what we glean from this in particular is that we need here this thing was needed. The dagger was needed. So when we first solved our first quantum mechanical problems, the free particle and the harmonic oscillator, we just took this from linear algebra, that if we work with column vectors, then we can apply a Hermitian conjugation to it, and then the column vector becomes a row vector, and the coefficients are the complex conjugates of the column vector. But remember, the physics is basis independent. And taking matrix elements and complex conjugating them and turning column into row vectors, that's all basis dependent stuff. That's all dependent on which choice of basis we make. So therefore, what we needed is, in order to express all those things also basis independently, we needed the abstract notion of Hermitian conjugation that maps from a vector space into its dual vector space. Remember, dual vector space. So we needed a operation, Hermitian conjugation operation, in order to get a scalar product, to get a scalar. Oh, so difficult to write when one cannot see what one is writing right away. Okay, so that's what we did. We therefore upgraded our definition of what is a complex vector space. Remember, we gave a completely abstract definition of what is a complex vector space that had, of course, column vectors as examples, but complex vector spaces are much more general. They could also be function spaces, for example. So we defined complex vector spaces, and then we added to the complex vector space more structure, because we needed here. We added the structure of Hermitian conjugation and scalar product. And then, remember, once we added these, we obtained then a way to Hermitian conjugate abstract vectors. So if this is a vector in our vector space, then we can take the Hermitian conjugate of it, and this we chose to give the name psi within a bra rather than a ket. So here we have that psi is an element of our vector space, and we have that the psi as a bra is an element of the dual vector space. Now, having added Hermitian conjugation and an inner product to our complex vector spaces, we obtained a pre-Hilbert space. So recall a complex vector space with a Hermitian conjugation and scalar or inner product is called a pre-Hilbert space. Now, in principle, one might think, okay, we are good now. As we went from the Hamiltonian to the equations of motion, canonical commutation relations to the solutions, and then boiled down the solutions to number value predictions. Along the way, we had to define complex vector spaces. We had to define along the way Hermitian conjugation and scalar product in order to make the predictions. And so now we have all of that abstractly, right? Not only in the particular form of column vectors, but abstractly, basis independently, we have all that. So we seem to be all set. Or are we? Not quite yet, because while we went from down this hierarchy of abstraction, all the way from the Hamiltonian to the number value predictions, there was one more thing we encountered, namely right here. We encountered that, recall, this is only possible in infinite dimensional vector spaces. Remember what it was? If you take the trace of the left-hand side of this equation, then you have the trace of xp minus the trace of px, which is vanishing because of the cyclic property of the trace. If you take the trace on the right-hand side, you get IH bar times the trace of the identity. But what is that? Well, that's IH bar times the dimension of the vector space. And so for finite dimensions, that's not going to work. But we did find that it does work for infinite dimensions. This means that it's not enough to just define a complex vector space that has Hermitian conjugation and a scalar product. No. These so-called pre-Hilbert spaces are not quite enough, because we are dealing here with infinite dimensional vector spaces. And for infinite dimensional vector spaces, we need to care about summing up infinitely many vectors and sequences of infinitely many vectors. And for that, we need the notions of convergence. So, for example, if you have an arbitrary vector in your vector space, in your pre-Hilbert space, then we want that it can be written as a linear combination of basis vectors, and we may need infinitely many of those. So in order to make sense of this, in order to make sense of the statement that this infinite sum of vectors converges to some other vectors, for example, infinite sum of multiples of basis vectors sums up to a particular vector, we need a notion of convergence. So therefore, we needed notion of it's so hard. We needed a notion of convergence. So what did we do there? First of all, namely in infinite dimensional vector spaces, I'm just writing up what I just said, need to be able to make sense of a statement like this, namely that we define a vector phi n to be the sum n equal 1 to capital N, and then some coefficients lambda n times some vectors psi n. So all we're doing here is something that you've seen in linear algebra all the time. We're just summing up some vectors psi n arbitrary vectors, psi n, with some coefficients lambda n, and we're going to get another vector in that vector space. That's fine. But what about, what is then the limit for n going to infinity, for example, of phi n, if it exists? So remember, the solution was solution is, first of all, in order to be able to define what is convergence, we need to know what is a distance, so that we can then say convergence we have if the distance between things goes to 0. So the definition was define distance, namely the distance between two vectors, psi and phi, was defined to be the length of the vector of the difference between the two, minus phi. Okay. And then we looked at what we want convergence to mean. So we say that a sequence of vectors, phi n, so I put a brackets around, right? And then we would write n equal 1 to infinity. This is a sequence of infinitely many vectors. And it is said to be Cauchy convergent, or a fundamental sequence, is called a fundamental sequence if it has the property that we think of as convergence. Intuitively, is called fundamental sequence if it obeys. And now I'm writing down the condition, and the condition is that you know, the vectors, the subsequent vectors, should get closer and closer together. So if the limit for n and m going to infinity of the distance between the phi n and the phi m is 0. Now, let me spell it out, what that really means. i.e., if for all epsilon larger 0, there exists a number r so that for all n and m which are larger than r, we have that the distance between the phi n and phi m is smaller than epsilon. Okay? So what this means is that, let's pick some epsilon. Like epsilon could be 10 to the minus 1,000. Really, really small. So which is a very small epsilon. Then this condition is that there ought to be a number r, capital R, such that all vectors whose index n and m is larger than r are closer than our epsilon, closer than 10 to the minus 100, right? So that means that no matter how small an epsilon you choose, some way down the line along this sequence, vectors, all subsequent vectors are closer than this distance, right? So that's what we mean, of course, by sequences converging, right? That's the intuition for a sequence to converge. Subsequent points, subsequent elements of the sequence get closer and closer together. And we want that, you know, that this is what convergence is supposed to mean. But it's not trivial that in your Pre-Hilbert space, such sequences actually have a vector against which they can converge, or towards which they can converge. If it is the case, if we've constructed our Hilbert space well, then we have that all these so-called fundamental sequences, also called Cauchy sequences, actually converge towards the vector in our space. So the definition was a pre-Hilbert space H. So it's a complex vector space with a complex Hermitian conjugation and a scalar product, is called a proper Hilbert space if all fundamental sequences made out of elements of H in H have a vector in H towards which they converge. So for example, if we have, so e.g., if the sequence of vectors phi n is fundamental, then there must exist a vector phi in the Hilbert space. Oh, all of these guys have to be elements of the Hilbert space. So if it is fundamental, then it has to exist a phi such that the limit for n going to infinity of the distance between the phi n and the vector phi goes to 0. And that's an ordinary convergence of numbers now, right? The distance between two vectors is the length. Oh, wait. This is a comma here. Such that this distance goes to 0. Okay. Now, where would this ever come up? You may wonder. What is this abstract stuff? What is that concretely? Well, concretely, let's look at the examples that we considered so far in that light. So we used to work without spelling it out with a pre-Hilbert space. Namely, we worked with the pre-Hilbert space of these column vectors, which had these entries here, psi1, psi2, right? And why is it the pre-Hilbert space? Well, let's be careful about it. Let's say we want to be on the safe ground of linear algebra. So let's assume that these column vectors have only a finite number of non-zero entries. So we worked with the pre-Hilbert space of column vectors, which have only a finite number of non-zero entries. This could be a lot of non-zero entries, right? So it could have, for example, the first million entries might be finite, and then the next gazillion entries are 0, and then there could be another billion non-zero entries. But at the end, at some point, it has to just be zeros, right? So that we have only a finite number of non-zero entries. They definitely form a pre-Hilbert space, right? Because they're a complex vector space for sure. But we also have the Hermitian conjugation, which consists of taking a transpose to take the column vector into a row vector and taking the complex conjugate of the components. So we have that. We have the inner product, the scalar product, by taking, column vector and contracting it with a row vector. So all of that is there. But is it a Hilbert space? It turns out that is not a Hilbert space, not yet. As long as we have the restriction, which is a reasonable restriction, that only a finite number of entries are non-zero, then we are on the safe ground of linear algebra, but that means we don't have a Hilbert space. Let me give you an example. I will write down now a sequence of vectors where every vector is in this pre-Hilbert space, but this sequence is a fundamental sequence, and yet it doesn't converge towards a vector in that pre-Hilbert space. For example, let's take the vector with entries 3, 0, 0, and the rest is 0. Now, the next vector in our sequence is going to have the entry 0, and then let's say 0.1, and then 0, 0, 0. The rest is all zeros. Now, the next vector has entries 3, 0.1, 0.1, 0, 0, 0. Forever zeros. And then the next one is, oh, sorry, that was a 0.01. And then we have 3, 0.1, 0.01, and then 0.001. And then the rest is zeros all the way. You see how this is going, right? What we have here is that this is a sequence of finite length vectors. And all of these, and the distance between these vectors gets smaller and smaller, right? The distance between this and that vector, arises from this 0.1 here, right? You take it's 0.1 squared. But the distance between this and that vector is only 0.01 squared, and so on. Sorry, it's actually 0.01. You take the square root of it, right? So as you go on like this forever, you find that this sequence of vectors here is, it's a Cauchy sequence. It's a fundamental sequence. But clearly, there is no vector in our Hilbert space towards this vector is converging, towards which this vector is converging. Because how would that vector have to look like? Well, clearly, the vector towards which this sequence is converging, so converges to, and in this case, we can easily read it off. It's just 3 and then 0.1, 0.01, 0.001, 0.0001, and so on. None of the entries are 0. All of the entries of this column vector are non-zero. And that's not a vector that is in our pre-Hilbert space, because the pre-Hilbert space consisted only of column vectors which had finitely many non-zero entries. So what we have to do is, in order to obtain a Hilbert space, is to include this vector, to add it to our pre-Hilbert space. So sorry. Okay, sorry about this, computer crashed. I lost some data. Okay, so what we needed to do is to add, this vector 3, 0.1, 0.01, etc. To our H. So you may wonder, okay, so we've made our vector space, our complex vector space, our inner product or scalar product space a bit larger by adding this one vector to it. But presumably that's not going to fix the problem. What is the set of vectors that we have to add to our vector space so that it becomes a Hilbert space? And what one can prove is, um, the the space of all column vectors that are square summable which means i.e. psi r star psi e sum over all I is smaller than infinity is a Hilbert space. Okay, this is why I had mentioned some lectures ago that we are going to work with the square summable coefficient vectors. I mean, with vectors that have square summable coefficients. They form a Hilbert space. And that means, technically speaking, that whenever we have convergence in the intuitive sense, namely that the entries get arbitrarily close to each other, then we actually have a vector towards which this sequence is convergent. This vector space, this Hilbert space, has a name. Is called, H is called little l2. Hilbert space of square summable sequences. All of this will be very important when we choose bases. So all this is important when we choose bases. In fact, the very notion of basis itself is non-trivial. And in Hilbert spaces, there is this notion of Hilbert bases. Let's see how this works. The definition is this. Definition: a set of orthonormal vectors let's call them Bn, in a Hilbert space, and this Hilbert space may be little l superscript 2, but it could also be any other Hilbert space, and I will tell you a bit about the zoo of Hilbert spaces in a moment. A set of orthonormal vectors in a Hilbert space H so they are obeying Bn, Bm equal to delta Nm. This is the Kronecker delta, Nm, is called a Hilbert basis. Hilbert basis in H if every vector in our Hilbert space can be uniquely represented as a linear combination of these orthonormal vectors. So if for all psi in the Hilbert space, there are unique coefficients. The unique coefficients psi n, and these guys are complex numbers, so that psi can be written as a sum over all n of the psi n coefficients and the Bn basis vectors. And since these are generally infinitely many terms, not necessarily, but usually infinitely many terms, therefore we need convergence. Right? That's why we needed all of this limit taking and defining distances and all of that. It's so that we can make sense of the very basic expression, namely that a vector can be expanded in a basis. If we have infinitely many basis vectors, then that expansion will involve infinitely many terms, and so therefore a limit. Namely, just to spell it out completely, this is equal to the limit for n going to infinity of the sum over n equal to 1 to capital N of psi n Bn, right? See, this expression here is just a vector. There is nothing non-trivial about it. It's just a vector, a linear combination of vectors. And so that vector here, right, we may call a capital N, for example. So what we're really saying here is that the limit for capital N going to infinity of this sequence of vectors is supposed to be that vector psi here. Right? So this is the convergence in the sense of a sequence of vectors converging towards a vector in the Hilbert space. And if we hadn't guaranteed that our pre-Hilbert space is a Hilbert space, if we didn't have enforced completeness, then we could have that this sequence is a fundamental sequence and yet no vector psi here. So we don't want that. Now, another definition about the nature of a Hilbert space. Namely, there are different kinds of Hilbert spaces. Definition. A Hilbert space H is called separable, if it possesses a Hilbert basis which is countable, so that we can count the first Hilbert basis vector, the second basis vector, the third basis vector, etc. Even if it's infinitely many, they need to be countable. If it possesses a Hilbert basis, that is countable. Not all Hilbert spaces have Hilbert bases that are countable. And so far, everything we did up to the definition of Hilbert space was forced upon us, right? We derived that there had to be an I in the canonical commutation relations. And we derived that the representations had to be infinite dimensional, that the vector spaces, our complex vector spaces, had to be infinite dimensional. We derived that there had to be a Hermitian conjugation and an inner product. All that led us to a pre-Hilbert space. And then we said, well, yeah, but we need completeness in this space so that we can work with bases. That led us to a Hilbert space. And now I'm telling you that there are different kinds of Hilbert spaces. There are Hilbert spaces for which the basis vectors are countable, and there are Hilbert spaces for which they are not countable. Right? Where the label at the basis vectors is not n equal 1, 2, 3, 4, 5, but for example, the real numbers. And the real numbers are not countable. There's no way you can devise a sequence that would run through all real numbers. All rational numbers you can do, but not all real numbers. And so we say that the cardinality is then higher than uncountable infinite. And there are even higher cardinalities, and there's no limit to how high the cardinality is. For example, one can prove that the cardinality of the set of subsets of a set is always larger than the cardinality of the set you started with. So for example, the set of subsets of the real line has a higher level of infinity, a higher cardinality than the real line itself. So you get a higher cardinality set. If you consider its set of subsets, even higher. And you have Hilbert spaces with bases of all of those cardinalities. You may wonder, okay, so what does nature do? It turns out, as far as quantum mechanics is concerned, not quantum field theory, but quantum mechanics of a finite number of particles, as long as we have just a finite number of particles, we get away with just working with separable Hilbert spaces. We believe that fundamentally, we should always be able to work with a separable Hilbert space. But quantum field theory indicates in principle that there are that the Hilbert space is of a higher cardinality. And yet, in practice, I mean, this goes beyond the topic of our course, but let me just tell you where this is all going. In practice, when we do quantum field theory, for example, quantum electrodynamics, then we usually truncate the system. And we put the field into a finite size or finite volume box, the electromagnetic field in a finite volume box. And then we say, okay, but not arbitrarily wavelengths are available to us in measurements. We can't really resolve wavelengths smaller than such and such. And when we do this, then even the quantum theory of the electromagnetic field can be described by a Hilbert space that is separable. In principle, for fields in free space without any kind of regulator, without any kind of cutoff, would have a non-separable Hilbert space. Okay, but for our purposes, for quantum mechanics, we can work with separable Hilbert spaces. Okay. Now I need to tell you a few curious facts about Hilbert spaces. Facts about Hilbert spaces. One of those curious facts is that for a given Hilbert space, all its Hilbert bases are of the same cardinality. So for a given Hilbert space, H, all of its Hilbert bases are of the same cardinality. This means that in quantum mechanics, in quantum mechanics of a finite number of particles, such as a finite number of electrons, we have that all of the Hilbert bases are countable. So in quantum mechanics, all Hilbert bases are countable. Remember, we have the Stone von Neumann theorem, which tells us that all representations of quantum mechanics happen in the same Hilbert space. The representations may look different, but fundamentally they just differ by a choice of bases. And now we have this theorem that all Hilbert bases are of the same cardinality, and in quantum mechanics that cardinality is countable infinite. This is curious for two reasons. One is that the Hilbert space the Hilbert bases, or we can just say the Hilbert space. The Hilbert space of a ton of material is the same size as the Hilbert space of one single electron. Why is that? Well, one electron has a Hilbert space which is countable infinite in size. All of its bases are countable infinite. But the same is true for a gazillion of electrons and a gazillion of protons and neutrons and all that. So countable infinite is countable infinite. That's Hilbert's hotel. If you have countably infinitely many rooms in your hotel, then you can put an arbitrary number of guests into your hotel. Did you know that? Imagine you're Hilbert and you run a hotel that has a countable infinite number of hotel rooms. And the hotel rooms are labeled number 1, room number 2, room number 3, all the way to room number infinity. And imagine business is going well. There's no pandemic, you have lots of tourists, your hotel is full. Every room is booked and occupied. And then a bus of tourists drives up to the curb of your hotel. And they get out of the bus, they go to the reception and say, we want to check in. And then you say, but my hotel is full. And they say, well, but we have a reservation. And then you say, no problem. There are 20 people on the bus. What do you tell the visitor, the guests that you already have at the hotel? Well, you tell the people in room number 1 to move into room number 21. The people in room number 2 are supposed to move into room number 22. And room 3 moves into room 23, etc. Everybody moves down by 20 places, by 20 rooms in your big hotel. And everybody can do that, infinitely many of them. And then the first 20 rooms are free. And you put the people from the bus in there, right? And in this way, it's also true that one electron has as many Hilbert space dimensions as does a ton of gold. Same thing, same size Hilbert space. So that's one curious fact. Another curious fact is this. As you know from your previous studies of quantum mechanics, there are continuous representations, right? You can represent your states in terms of position and momentum wave functions, for example. We will soon cover what they really are in more detail, but you already, of course, know that. And you may wonder, what about this? Don't we say that we have a position basis and a momentum basis, but they are continuous? How does this compute? Well, as we will see, we'll see that there how to say it? Well, we'll see that what we can do is a formula which I will write for now like this. We can write we can often write our vectors in the Hilbert space not as sums of linear combinations of Hilbert basis vectors, but also as integrals over such a function of coefficients, psi of mu, and then a continuum of vectors. Now, all of this so far we haven't really defined yet. How do we integrate over vectors and things like that? So we will have to do this carefully. But let me tell you already that there's a price to pay for this. These guys are not normalizable. Not normalizable. So therefore, and they are not in L2, so not in our Hilbert space. So they form kind of a basis in quotation marks, but truly, mathematically speaking, they're not a basis. It's something slightly different than that, because these guys are not actually in the Hilbert space. We will later see how all of this can be fixed in terms of projectors and so on. So finally, we are ready to do what we set out to do. Namely, we want to be able to move freely between abstract formulations of our vectors and linear maps in the Hilbert space on one hand, where things are uncluttered and clear, and on the other hand, the representations of these vectors and linear maps in a basis. The bases have the advantage that they contain coefficients that are numbers, and they contain concrete matrices or operators of some form that are concrete, mathematically concrete, and we can do things with them. For example, we may write down differential equations and then apply tools from the differential equations theory to solve problems. You see, the overall business in quantum mechanics is that on one hand, the physics plays out on the abstract level of abstract vectors in your Hilbert space and abstract linear maps that map those vectors into other vectors. And it's good to understand what's going on. But if you want to calculate something concretely, so if you want to make headway mathematically, then it pays to represent these things in a basis where the coefficients are numbers. Where the coefficients of the vectors and the coefficients of the linear maps are numbers and functions, and then you can differentiate and sum and do all the useful things there. Okay, so we are now ready to do this. We are now able to freely move between the abstract and the concrete representations. So now, how do we do this? Now we can move between abstract x hat, p hat, and psi, and concrete representations in bases. And some bases might be useful for one purpose and another basis for another. How? Well, it works like this. Assume we have a Hilbert basis. Assume the Bn are a Hilbert basis. And remember, in quantum mechanics, the Hilbert space is separable. Therefore, the Hilbert basis is countable. and the n's really run through the integers, or the positive integers, for example. So assume a Hilbert basis, singular. So assume that these are a Hilbert basis. So this means every psi in H can, this is an in symbol, can be written as psi equal to sum over n equal 1 to infinity psi n bn. Remember, this is the definition of what is a Hilbert basis. A Hilbert basis is a bunch of vectors that are orthonormal and such that every psi can be represented in this way. But then, what are the coefficients? Here, these guys. What are they? Well, to find out, apply a vector bm from the left. So then what do we obtain? We obtain that bm psi, this is a scalar product, right? So this whole thing here, this is an element of C, is equal to, and then here we have bm sum n over all n psi n bn. And this then we can write as some as a bm. Oh, no. We can write this a bit more nicely, like this already. Sum over n, and then it's the bm psi n bn. But since this is an element of C, by linearity, we can pull this thing out. So this is sum over n psi n bm bn. This is Kronecker delta mn by orthogonality of Hilbert basis. And therefore, this is psi m. So we have, therefore we have that psi m equal to bm psi, right? We're just putting together what we had here. Bm psi equal to blah blah psi m. Okay. Oh no, terrible. Let's put it this way. So very important formula, and this leads to a definition. These coefficients, the coefficients psi m, which are the scalar product of our vector psi with the basis vector bm, are called the wave function of the abstract vector psi in the basis. And when we say basis, we will always mean Hilbert basis now, in the basis of the bm. Let me give you a bit of a preview that might remind you of things you've seen in previous course of quantum mechanics, preview and review. We will also use continuous spaces. Of course, they are not actually bases because these vectors are not normalizable. Therefore, they are not in the Hilbert space. For example, a basis of vectors mu, where, for example, the mu are running through the real numbers. It's just an example. And these guys are not normalizable. Then we can do formally the same thing, except that we will have to clarify certain caveats later in the course. Then we have that the abstract vector psi can also be written as a linear combination of these basis vectors with coefficients psi mu. Now that label is no longer psi n discrete, but psi mu is a continuous label. And then we have here these basis vectors, and instead of summing, we're integrating now, so we have a d mu. But as I said, we have, oh, let me put a prime on here. As I said, we have not yet defined what we mean by summing, integrating over vectors. We know how to sum over them, but not how to integrate over them. So this is still pretty formal stuff. But we can then again ask, what is this? What are these coefficients? And then we can again apply the basis vectors from the left. So again, apply basis from left. From the left, namely, the basis vectors are now called mu. So now we have here mu psi equal to integral minus infinity to infinity. And then we have here mu, coefficient psi mu, mu prime, d mu. Now this here is just a complex number. We can again pull this out. So we have the integral from minus infinity to infinity, and then we have here psi mu, and then we have mu, mu prime, d mu prime. Now, these guys are also normal, turns out, but also normal with respect to what is called the continuums normalization. So it's delta of mu minus mu prime. This is a Dirac delta. Which I'm sure you've seen before. And that means that we obtain then that this is equal to integral over r psi mu delta mu minus mu prime d mu. So this is psi mu. And we define this to be psi of mu, right? Whenever we have something with a continuous index, then we tend to write this as psi of mu. But it's the same thing whether we write psi of mu or psi subscript mu, same thing. But this is, of course, the way you know it, right? So now we have that definition. We have that now psi is equal to the integral over r of psi of mu, mu de mu, right? And we have that psi mu, no, let me write it now in there. Let me write it down here. And up, psi mu. And we have that psi of mu equal to mu psi. And we say that psi of mu is the wave function of psi in the mu bases. So what we see is that the same vector psi can have discrete representations in terms of a discrete wave function of coefficients psi n when we choose a proper Hilbert basis. But when we choose a continuum basis, then we get a wave function psi of mu. And there are many continuous bases, and there are many proper Hilbert bases. And so the key thing to take away from this is that if you look at a particular vector in the Hilbert space, that particular vector describes the initial state of some physical system. And as such, that vector is basis independent, right? It's a thing. It's this set of initial conditions. But you can look at this vector in whatever basis you want, any Hilbert basis, which means you get discrete coefficients, or any one of these continuum spaces, and you get some wave function. So the same vector has plenty of different wave functions, and they're all equivalent. They only differ by a choice of bases. Okay, so this is as far as we get today.